My name is Berzin Bhavnagri, and I'm talking about an index of carcinogenesis using pairwise consistency. An index is developed for elements and molecules applied to study carcinogenic substances identified in studies on humans or primates. In other words, cancer-causing substances. The index will be found to be significantly different between carcinogenic and non-carcinogenic chemicals tested on rhesus monkeys. These animals are possibly the closest thing to humans. This work is based on an existing theory of how some chemicals cause damage to living cells, in that free radicals can react with other molecules to cause cell damage or DNA mutation. The index can be used to extend the theory of how chemicals may cause damage to living cells. Based on the value of the index calculated from a molecule, that molecule can react with other molecules to cause cell damage or DNA mutation. To apply pairwise consistency to relativistic quantum mechanics. In quantum mechanics, each molecule under consideration can be thought of as a wave function from a Hilbert space. The Hilbert space of the wave function with odd half spin will be shown not to be pairwise consistent. On the other hand, the lens space L3Q is pairwise consistent if Q is relatively primed to 3. We defined the above index based on a function that is sensitive to both spin parity, i.e. whether odd or even, and whether it is relatively primed to 3, the space dimensions. So we come to the definition of pairwise consistency. Pairwise consistency means that this operator is one-to-one for all quantum symmetries from S. In general, pairwise consistency is defined for any set of axioms, any specified set of axioms to be called S, and a set of monomorphisms defined on that space S. R1 and R2 are any two of the monomorphisms, and the target of those monomorphisms is in fact entirely arbitrary. The operator takes the two monomorphisms and constructs another function as its value. It encloses each value of the two monomorphisms within a set, and then takes the union of the two. So we specialize this general formulation to a space of wave functions of an atom or molecule subject to either the Schrödinger or the Dirac equation. We take a quantum symmetry to be a monomorphism, and the symmetry group called the Heisenberg group of the one-dimensional quantum harmonic oscillator consists of matrices of this form. The harmonic oscillator describes molecular orbitals. Here is the time-independent Hamiltonian, which is defined by the first formula. In it you have the momentum operator defined on the second line. M is the mass, omega is the frequency of the oscillator, and x is the position variable. The wave functions psi are the solutions to the time-independent differential equation H psi equals E psi, where E is an energy scalar. and H is the Hamiltonian. Now this is the non-relativistic or Schrödinger equation. If we substitute the Dirac operator for the Hamiltonian, we instead have the Dirac equation, which is a relativistic analog of the Schrödinger equation. So now we come to the weak consistency, the weak representational or pairwise consistency of quantum mechanics. We have the following theorem. The Heisenberg group has no elements of finite order. The consequence of this theorem is that the Heisenberg group has no involutions. And in previous work we proved an existence theorem which under two conditions on the automorphisms of a space will guarantee their pairwise, the space is pairwise consistent, and those two conditions are that the automorphisms act freely, and firstly that the automorphisms act freely, and the second that the automorphisms contain no involutions. Now the second of those two conditions is sufficient but also necessary. So we can say that that since the Heisenberg group has no involutions, that quantum mechanics is weak pairwise consistent. Now we come to a second theorem, which is the relativistic case, unlike the previous case. For a spin Hilbert space whose automorphism group acts freely and never maps a spin state to its orthogonal spin state, its representations are pairwise consistent. So the theorem above allows us to deduce that the electron cannot be pairwise consistent because the exchange antisymmetry maps the minus a half spin to the plus a half spin, or vice versa, and the minus a half and the plus a half spins are orthogonal. Also, tensor products of electrons with spin half n and odd n are not pairwise consistent either. And the consequence of these is that free radicals cannot be pairwise consistent. So we come to the pairwise consistency of the length space. We have the following theorem, that the length space is L3Q with Q greater than 2 but relatively prime to 3 are pairwise consistent with respect to the structure of isometries. Now this theorem uses the previously mentioned existence theorem, and the length space actually satisfies both the conditions of the existence theorem. So the length theorem is actually pairwise consistent if the Q is relatively prime to 3. So this leads us to the following definition. If Q is the total number of electrons, we define the index to be Q modulo 3. To the definition, if Q is the total number of electrons, we define the index to be Q modulo 3. So now we come to examples of substances. Firstly, we look at the major components of the air. Now to explain how the index is calculated, we simply, to take the case of nitrogen first, we simply look up nitrogen in the periodic table. Its atomic number is 7. Since there are 2 nitrogen atoms, we multiply that by 2. So nitrogen has the dimer has 14 electrons. We then divide 14 by 3, and the remainder is 2. So that's the index. In the case of oxygen, oxygen has atomic number of 8. There are 2 oxygen atoms in the oxygen dimer, in the oxygen molecule. So it has a total number of electrons of 16. Dividing by 3 and taking the remainder, we are left with 1, which is the value of the index. Now, the thing that is extraordinary about this table is that the only components of air with a 0 index are noble gases, with the single exception of ozone. So that leads one to suspect that there is something special about a positive index, and so I looked up a database called the carcinogenic potency database and computed the index for the rhesus monkey database. So these are cancer-causing molecules or suspected carcinogens, and the carcinogenic potency database, the authors have developed a statistic called TD50. In this table, if TD50 is reported by them to be not statistically significant, the cell is blank, and otherwise a value is recorded. So, for example, aflatoxin B1 was found to be carcinogenic, and it has an index of 0. I'm sorry, but the full table does not fit on the slide. So I performed a statistical analysis, a 2x2 contingency analysis, and here it is. Make the null hypothesis. The index is not significantly different between carcinogenic and non-carcinogenic chemicals. So firstly, we compute the observed cell frequency table. For example, the case of index equals 0 and carcinogen, whereby that I mean that TD50 was found in the potency database to be greater than 0. There are 4 of those in the table. Likewise, with index 0, there were 4 non-carcinogens in the table. With an index greater than 0, there was only 1 carcinogen in the table, and with an index greater than 0, there were 10 which were not experimentally found to be carcinogens. Now, the majority of the weight lies on the diagonal. So then we compute the expected cell frequency table, which is as follows. And from this, the value of chi-squared, which is 3.997, comparing it at a significance level of 0.05, is greater than the tabulated 5% chi-squared value of 3.84. So we reject the null hypothesis. So in summary, the result is that the index is found to be significantly different between carcinogenic and non-carcinogenic chemicals tested on rhesus monkeys. The index can be used to extend the free radical theory of how chemicals may cause damage to living cells. Based on the value of the index calculated from a molecule, more specifically if the index is 0, that molecule can react with other molecules to cause cell damage or DNA mutation. Thank you.